We've been looking at different types of data sets, and in particular different features of data sets like the mean and the standard deviation, the center of the data and the spread of the data. So now we're going to look at a very specific and common type of data set called the normal distribution. A normal distribution just generally is data that is bell-shaped, and here I have just a very rough example. Bell-shaped with the data clustering around the mean. So if you think about this kind of like a frequency distribution or a histogram, where really you'd have a bunch of bars in here, but they get taller as you get closer to the mean because there's more and more data items near the mean. And the farther you get from the mean, the more rare those data items become, okay? Now this bell curve is really just kind of connecting all the dots, or all the tops, I should say, of the bars in a frequency distribution. If you had a lot of different bars, it would look like a smooth curve, and eventually you could approximate it as a smooth curve, like so. So it has this bell shape, okay, or a normal curve. Normal distribution. And so some examples of normal distributions. The sum of two die rolls. So if you have two die and you roll them and you add the two numbers up, you'll get a normal distribution where the mean is 7. And you know the number of ways you can get a 7 are the most common, and then 6 and 8 are next, and then 5 and 9 are next after that, and so on. So you get 1 and 12 are the hardest ones to get. You either have to get a pair of 2 and 12 are the hardest to get. You need a pair of 1s or a pair of 6s, and those are the only ways to get those. So that would follow normal distribution. Birth weight of newborn babies. Okay, they again cluster around the middle. Female shoe sizes. You can see these examples popping up. Blood pressure, SAT scores, mature buck antler scores. So for hunters out there, if you take the antler scores, and that includes different lengths and spread and length of tines and circumferences of the main beam and stuff, and you score those and add those up, they actually follow a normal distribution as well. So lots of different things. Spanning many different subject areas, okay? So you see these in medicine, in economics, in science, all over the place. And so this is a very, very applicable topic, and obviously, etc. So lots of different things you could have. So what's interesting then about the normal distribution is that you can start to sort of estimate how many data items are near the mean and how close they are based upon our standard deviation. We've talked about the standard deviation before. The standard deviation gives you kind of the spread of the data, but you can kind of group things together. If you were to go within one standard deviation of the mean on either side, so whatever the S is, let's say X bar is the mean, and S is standard deviation. Okay, then the value of S is the distance from the mean. The bigger S is, the wider the distribution. You could have a distribution that is wider but not as tall, so things that are more spread out. That would be a larger standard deviation. If you have a smaller standard deviation, you get more of a spike in the middle because everything is very tight and clustered to the mean. Okay. Now, in theory, the standard deviation will give you, if you go one standard deviation on either side, so if you add S or subtract S from the mean, that will typically give you about 68% of all the data in a set, or in a sample. And so, especially the larger those samples get, the more likely you are to be around 68%. Okay, so within one standard deviation, you'll tend to have approximately 68% of the data items within one standard deviation on either side of the mean, okay? If we wanted to go to 2 standard deviations, so if you were to add 2s or subtract 2s, put that out here somewhere, so add 2s or subtract off 2s, then in theory you'll get about 95%, I think it's 95, right? Yeah, 95% of all the data values in or within 2 standard deviations. Ooh, I drew that kind of far. Actually, let's make this go up. Okay, so within that region, you would have about 95% of all the data within 2 standard deviations. And if you really want to encompass just about all the data, you can go 3 standard deviations on either side. And that typically gathers about 99.7% of all the data items within any normal distribution. Okay, so if you were to go, and I'm running out of room, so I'll go x bar minus 3s, and over here it'd be, that might be too far, x bar plus 3s, right? So you add 3s and subtract 3s, then within that region you would have approximately, and I'm doing this kind of rough here, approximately 99.7% of all the data within that sample, okay? So we have some really good estimates now, especially if you get larger data sets. These approximations become much better, okay? It won't always be perfect. You could get 80% of your data within 1 standard deviation, or if it was real tight but you had a few outliers or something that might move the standard deviation out, you could really get that, you could get more values in there. But over time, with a larger distribution or a larger sample, these 3 percentages will be pretty close.